researchers successfully converted a kidney from blood type A to universal type O and transplanted it into a brain-dead person, marking a major step toward expanding access to donor organs. In a new study published in Nature Biomedical Engineering, scientists used a special enzyme treatment to strip away the blood type markers that usually cause rejection, turning a type A kidney into what they call an enzyme-converted O, or ECO, kidney. Normally, organ transplants require blood type matches between donor and recipient to avoid immune system attacks, especially for people with type O blood, who can only receive type O organs. These patients make up more than half of the transplant waiting list and often wait years longer for a match. The researchers used a method developed in 2022 to remove antigens from organs using enzymes mixed into a perfusion fluid. In this case, they applied the treatment to a type A kidney and then transplanted it into a brain-dead patient who had type O blood and naturally high levels of anti-A antibodies. The team didn't give the usual antibody-suppressing drugs used before transplants, as they wanted to see whether the ECO treatment alone would be enough to delay rejection. For 2 days, the kidney worked without issue, showing no signs of rejection. On day 3, however, the organ began producing new type A antigens, and the immune system started to respond. This was expected, and researchers say that in a real clinical transplant, standard drugs could help manage this later response. While the ECO kidney wasn't long-lasting, it avoided early rejection, showing promise for expanding access to donor organs.
Scientists have created bandages made from living fungi that could one day help heal wounds and repair human tissue, thanks to a common soil mold called Marquendomyces marquandii. In a new study from the University of Utah, researchers found that this fungus can naturally grow into a soft, flexible, water-rich material called a hydrogel, something that closely mimics the texture and structure of human skin, cartilage, and other soft tissues. Hydrogels are already being explored for use in medicine because they're soft, moist, and biocompatible, making them ideal for things like tissue repair, wound dressings, or even scaffolds to grow new cells. What makes this particular hydrogel exciting is that it's alive and grows itself, creating a multi-layered structure with different levels of porosity. Basically, it forms a sponge-like material that changes based on how and where it grows. Unlike other fungi tested for similar uses, Marquendomyces marquandii forms thick, layered sheets that can hold up to 83% water and maintain their structure without becoming brittle or drying out. The researchers discovered that by adjusting the growing conditions, like oxygen levels and temperature, they could control the material's properties, making it more or less porous depending on the medical need. That flexibility could make it useful not only for skin grafts and wound healing, but potentially even as a base for bone repair, thanks to its main component, chitin, a natural substance also found in seashells and insect exoskeletons. While the material shows real promise, scientists stress that this is still in the very early stages.
A new vaccine shows promise in preventing up to 88% of aggressive cancers, like melanoma, pancreatic cancer, and triple-negative breast cancer, according to a recent study from researchers at University of Massachusetts Amherst. Using tiny lipid nanoparticles packed with 2 immune-boosting molecules, the vaccine trains both arms of the immune system to recognize and destroy tumor cells. These nanoparticles trigger a fast, general response from the innate immune system, and a slower, more targeted attack from the adaptive immune system, which creates memory for long-term protection. In tests on mice, the vaccine was injected under the skin on a schedule of 3 doses and paired with either tumor-specific peptides or full tumor protein mixtures. When tested against 3 challenging cancer types, the results were striking. Mice receiving the full vaccine completely rejected tumors, while untreated mice, or those with a single adjuvant, died within weeks. Even more impressive, mice that survived the first round stayed tumor-free when re-exposed to cancer months later, showing strong immune memory. The particles effectively reached lymph nodes, critical sites for triggering immune responses, and activated key messenger cells that stimulate both T cells and B cells, the main players in killing cancer cells and remembering them. When the vaccine used whole tumor lysate instead of isolated peptides, it still protected 69% to 88% of mice across all cancer types tested, and all vaccinated mice survived a second cancer challenge. This broad protection suggests the vaccine could work across multiple cancers, not just one.